I am going to invite Professor Qiben Yan to the stage, and he will be talking about his participation in the Mcity AV Challenge. Michigan State University was the U.S. winner of the Mcity AV Challenge. So take it away.
This is proof that we're non-biased, right? We've got Michigan State up there on the. That's great.
Exactly. Hi, everyone. This is Qiben Yan. I'm an associate professor at Michigan State. I'm so glad to introduce our Mcity challenge solution. We call it safety first, rule-based decision making. My research area is actually cybersecurity. So prior to this challenge, we have no experience on traffic control and decision making, but Mcity makes it really easy for us to test our algorithms and evaluate our solution, and we really appreciate that. So our team consists of 2 undergraduate students and 1 graduate student and myself. We are from computer science department. Our team is called Spartans. So this challenge asks us to develop a decision-making module for this autonomous vehicle. And this decision-making module will decide the vehicle's actions. And basically, we are going to make real-time choices based on the current situation to guide this autonomous vehicle through very complicated routes in the Mcity. And we are provided with a test environment and a base AV decision module. We are going to change the decision module to develop our own algorithm to navigate this process. So in our solution, our goal is really to prioritize safety and smooth driving, because the criteria of this challenge is first the safety and the comfort of the driver, and also the successful completion of the passes. And inside this driving scenario, we have to deal with very dynamic obstacles and challenging like intersections and roundabouts. And this makes our solution very difficult. So we have to traverse the environment safely without any accident. And we have several development iterations. In our first iteration, we do a rule-based approach using only the vehicle information and the traffic information. So it will not like deaccelerate when it saws a roundabout. It will also not take into consideration of surrounding vehicles. And in our second solution iteration, we develop a slow approach that using the predicted upcoming waypoints information. So that makes us a conservative approach that will drive slowly through all the complicated traffic scenarios. And our final approach will predict the jerk values at future points to accurately predict when and how much to accelerate and deaccelerate. And this makes our solution really safe, and it's provide like maximal comfort to the drivers. But at the same time that we are also being a little bit conservative during those roundabouts. And finally, we are resort to those learning-based approach to try to address the edge cases and dynamic scenarios, but we will not be able to finish that. So here's our overall design. We have taken the vehicle state and the map and traffic signal information as input. And then the first stage of algorithm is we do a state orientation, reorientation to adjust the vehicle's positions and orientation to make sure that it's getting ready for the next action. And then we will predict the look-ahead waypoints to do the dynamic look-ahead adaptation. And finally, we'll do the acceleration control to see how much we're going to accelerate and how much we are going to deaccelerate. So here are 3 key mechanisms related to this 3 stage. First is kinetics control. In the kinetics control, we are basically going to perform the state reorientation to get the vehicle ready for the upcoming traffic conditions. And the second main algorithm is the proximity waypoint tracking. So we are tracking the surrounding vehicle information and the surrounding traffic conditions, and also the map and routes information to make the decision for the next waypoint that the car is driving into. And finally is upcoming waypoints window. So we are moving the window ahead of the vehicle to say like where are we going to in future. So that will make us much more effective in predicting the traffic and to decide when we are going to deaccelerate and accelerate. So now gets a little bit into the kinematic adjustment. We first check the maximal speed and the maximal acceleration that was allowed to give the maximal comfort to the drivers. That gave us a limitation to the orientation change to avoid the drastic changes. And then we will predict the vehicle speed at a stop sign and with other vehicles. For example, when there will be potential traffic conditions ahead of us, we will be slowing down the vehicles ahead of time to make sure that we are not getting into any traffic accident. And for the proximity waypoint tracking, so the vehicle will, our algorithm will track several waypoints in a round circle around this test vehicle to see what are the traffic conditions and what are the next potential waypoints that can give us the maximal speed going forward. And those data will be used to decide whether we want to accelerate or deaccelerate, basically to allow for a smooth turning during these roundabouts. And there's a consecutive roundabouts, so we have to consider like multiple roundabouts conditions to decide for the next waypoints. And finally, for the upcoming waypoint window, we will basically making the round circle larger to check a moving window of the upcoming change of in orientation. And finally, based on this data, we will make prediction for the upcoming jerk and acceleration. And this makes us like very efficient in running the course of the traffic. And also when we are coming ahead before this roundabout, we will try to slow down the car ahead of the time. This is to emulate driver's vision. Right? When they see there's a roundabout ahead of the vehicle, they will slow down and well before when they reach the roundabout. So in the end, we got this second place. We have probably the best safety score and rule compliance, traffic rule compliance, and also the comfort of the driver. But we are a bit lower on the efficiency and the trajectory completion. So you are going to say in the demo that we are still a little bit of conservative during those driving in the roundabouts. And what makes us a challenge is that it's not very easy to accurately predict the vehicle positions in the future. And also it's not so easy to navigate consecutive sharp turns like very efficiently. So sometimes we are being too conservative just to avoid any dynamic traffic accident conditions and traffic accident. And also it's challenging for us to detect the vehicles following behind of us. So we need to make some adjustment to our algorithm to make sure that we are safe. So for the future improvement, we will be improving our prediction algorithms and also doing smoother turnings, add more logic to deal with the edge cases such as multiple roundabouts and tight turns. And also we are going to better compensate for the control errors in the real vehicles. Yeah, really want to thank the Mcity team for providing this fantastic challenge for us. We really learned a lot. So now let's get into the demo. So the demo was run on the remote site at Michigan State. My student is sitting in my lab in East Lansing. So here on the dashboard, you can see on the right-hand side, we have the simulated traffic conditions. And we also have the throttle information and the brake. On the left corner, on the left down corner, you can see the roadside camera. And on left-hand side is the real vehicle. Now I guess our vehicle is starting. So now the vehicle is loaded with our decision-making module. It's going to run the course of this traffic condition. So you can see it measures like whether there's a car ahead of us, and it will try to accelerate and deaccelerate. So right now it's following the traffic and try to accelerate through this this line of the passes. Yeah, on the left bottom, you can see this is our the real vehicle that was driving. Now we are reaching the roundabouts. So before we reach the roundabout, and we are going to deaccelerate the vehicle to make sure that we have the maximal safety and comfort. So now the vehicle is entering the roundabout. And after entering the roundabout, the vehicle will accelerate a little bit, but it's still like within the limit of the traffic speed. But you can see that in this roundabout right now, our vehicle is driving slowly. Right? This is to make sure that we are not getting into any dynamic traffic conditions in traffic accident. And it will take a little bit of time for the vehicle to drive through this roundabout. So you can see that in our algorithm right now, like it's not have a good prediction of the follow-up traffics. So if we have a good prediction of that, we could probably switch to another lane or driving much more aggressively. So now it's try to exit the roundabout. And after it starting seeing that the vehicle is going out of the roundabout, it starts accelerating. You can see the throttle was pressed, and it started accelerating and driving through these passes. During this straight line, it's following the maximal traffic speed so that it will drive more efficiently. Yeah. After it reaching the end of the road, then I believe the control will stop. Yeah. So here is our demo for the decision making. Thank you everyone for enjoying this show. I'm happy to take any questions.
I'm just curious. Oh, first, excellent presentation. What's particularly challenging for your algorithm for the roundabout?
For the roundabout?
Yeah, why it's so slow?
Yeah, so the particular challenge is really to control the vehicle like positions and the jerk rate. So it's really difficult when you accelerate a little bit. It's reaching the maximal jerk rate, so the vehicle will give us warnings. So we have to really make it a little bit conservative. But I mean, there's definitely improvement that we can do to consider like the traffic behind us and the angle of the roundabout to make it more efficiently. So right now, this rule-based decision making is being conservative to make sure it's being comfortable and maximum the safety profile. Yeah.
But don't worry, we're going to hold some more of these events, so he'll get another shot. Yeah. Other questions? Okay. Thank you very much, Professor.
Thank you, everyone.
Appreciate it.
Thank you, Professor Yan, for your participation, and great to have in-state team to join us at the Autonomous Vehicle Challenge. I want to mention that there were 24 teams participated around the globe for the Mcity Autonomous Challenge, and there's actually another top 5 teams in the audience. Professor Yiheng Feng from Purdue University, they are number 4 in the challenge. By the way, I want to mention the challenge is also ongoing, although we closed the challenge for the top 10 teams by August 1st, but we open this continue, we still receiving submissions, and then we update the leaderboard about every month. So if for the students and research teams, if you have interest, you can still go on and to look at the Mcity Autonomous Vehicle Challenge, and then you can submit your submission, your algorithm for testing, and then we will post the result about every month. So that's still ongoing.